All right, I think we'll make a start. Welcome to today's GCSE Chemistry session. We're going to focus on crude oil and fuels, and then all the chemical subtopics that you'll need to know to fully understand everything you need to know about crude oils. Excuse me. Now, the important thing about this topic is that you have a good, solid understanding of the basics. So to this end, you're going to need to interact. So you can use the chat. You know that when you do type things in the chat, it directly comes to me. No one else can see what you've put in there. So don't worry about anyone else seeing what you've put there, because I know it can be a little bit daunting sometimes to put something in the chat and everyone see what you've put. But it is really important that you do interact so that you do get a full understanding, because this is the best way to tackle this topic. You get your solid base understanding, and then everything else during your exams will come naturally, and you can go through logical processes to answer any question to a high degree. All right, so today we're going to go over crude oil and fuels. We'll focus on hydrocarbons, then we'll look at the fractional distillation of oil, burning hydrocarbon fuels, cracking hydrocarbons, and then the second topic of today would be organic reactions, alkanes, alkenes, and alcohols. So in terms of the timetable for today, we don't really stick to this, to be honest. I'll just see how we go. We might be going faster or slower dependent, but you will get breaks and obviously lunch as well. Now during the session, as it says here, please do ask questions. If you have any, we won't be doing Kahoot sessions, but we will have exam questions throughout. If you do want me to go over another concept again, just put it in the chat, and I will be more than happy to do so. All right, so the first thing that we're going to focus on is, let me just get this right. Move that there. That. All right, so today we're focusing on crude oil. It's basically looks like this. It's like murky, black, it's thick, but it's really, really useful, and we use it for many different things. It's used for fuel. That's probably one of the main uses of crude oil, but we can also use it to make plastics and so on. Now, focusing on hydrocarbons, crude oil is essentially made up of two things. It's made up of carbon and hydrogen. And then logically, you can take from this that they're made out of hydrocarbons. Now, the reason that we use hydrocarbons is because, obviously, as you know, we're a carbon-based life form, and that means that carbon is very versatile. It can form a lot of compounds, including of crude oil, and then we can fractionally distillate this to create other substances and compounds, which are also equally as useful. Now, carbon atoms, as I said, are very versatile. The way it does this, they can bond to each other, they can form chains, rings, and then these carbon chains and rings form the skeletons of most organic molecules. Now, obviously, we all know the periodic table. I'll start from the basics again, because as I said, fully understanding this all the way through is probably most important. So when focusing on crude oil, we're focusing on carbon. We have, looking at the periodic table, we have metals on the left, we have non-metals on the right. And so as you can see, carbon sits on the right and it's a non-metal. All right, this is what carbon looks like in the periodic table. In the chat, can people tell me what the top number indicates? So on a periodic table, all elements come in this format. They'll have their elemental symbol and then a top number and a bottom number. So in the chat, just type in what is the top number indicating. I'm not going to move on unless the majority of you do it. So, because I really think it's important to understand everything that's going on in this topic. Yeah, all right. So the top one is mass number, and the bottom one, which is that, type in the chat quickly, and then we'll move on. Whilst you are doing that, on the right, we see the atomic structure of carbon. We have 6 protons, 6 neutrons in the nucleus, and then there are 1, 2, 3, 4, 5, 6 electrons. Yeah, the bottom number is atomic number. And so remember that it helps, obviously, when you're looking at the atomic structure. Remember that electrons in the rings, we have 2 in the first ring and then 4 in the outer ring. And then this is important when looking at covalent bonding. Right, so carbon is in group 4 on the periodic table. This means it has 4 electrons in its outer shell. And as I said before, carbon covalently bonds. And since it has its outer shell, 4 available covalent bonds for each carbon atom can form. These covalent bonds could be single, double, and sometimes even triple bonds. And for each of them, 1 electron is shared. Carbon atoms can bond to each other, and these can form long chains using these outer electrons. Now, as I said before, a hydrocarbon is a compound containing carbon and hydrogen only. This only is quite important in terms of exam techniques. So you might get a question which says define a hydrocarbon. A lot of people will just say hydrocarbon is a compound containing carbon and hydrogen and then leave it. But the fact that it only contains carbon and hydrogen is essential. So make sure you put that only at the end. At the bottom, we have a few examples of hydrocarbons. As you can see, there are only 2 elements in it, and so can be defined as such. Right, looking at alkanes. This is one of the most common groups of hydrocarbons. All their names end in ANE, so they're all anes. The first part of the name of each alkane tells you how many carbon atoms are in its molecule. So methane indicates that there's 1 carbon atom, ethane, 2, propane, 3, butane, 4. And these prefixes run throughout alkanes and alkenes and some other hydrocarbons as well. So the chemical structure of methane, as we said, it has 1 carbon. And as you know, carbon has 4 covalent bonds, so there'll be 4 hydrogens connected to it. Ethane, same principle, 2 carbons, 4 covalent bonds, but remember the carbons do need to link. So they take up one covalent bond between them. And this means that there are only 3 available covalent bonds on each carbon for the hydrogens. Same for propane and butane. It just follows the principle, and I'm sure you will know this. Now, if you do forget the order of these, because I know meth, eth, prop, and butes, they don't really have any relation to the carbon numbers, so 1, 2, 3, and 4. You can make some of these things. So monkeys eat peanut butter. That's a common one. You can come up with your own, or you can come up with your own strategy of learning them as well. So I had a really, really weird one that M was for mono, which is 1, and so on. I won't bore you with the rest, but it can be as weird as you want, as long as you do remember it. Now, alkanes are known as saturated hydrocarbons. What does saturated mean? Type it in the chat. If someone tells you that this compound is saturated, what would that indicate? How many of you are there? There are about 9 of you. As I said before, I'm not going to move on until the majority of you answer, because it is important that you fully understand this topic. Yeah. Right, I have a variety of answers here. Saturated means that you can't attach any more. So there are no more bonds that can be used or added. So there are a few answers there which aren't quite correct. So just remember that saturated means that you can't attach any more bonds. Yeah, it doesn't mean anything else. In the topic of hydrocarbons, it means that yes, every carbon bond has been used. If there are double or triple bonds, this is not a saturated hydrocarbon, because there is the ability to attach another element so that there are 4 single bonds. Now, this means that they contain as many hydrogen atoms as possible in each molecule. This is specific to saturated hydrocarbons. But in GCSE, this is probably the only time that you find the word saturated in terms of chemical compounds. Obviously, you'll have a saturated solution, which is a little bit different, but it follows the same principle. So saturated means that you can't attach anymore. All the bonds need to be single covalent bonds. Right. The general formula for alkane molecules can be written as this. We have Cn, so how many carbon molecules you have. And then to calculate the amount of hydrogen molecules, remember it's saturated, you have H, and then it's 2N plus 2. So you just double the amount of carbons, and then you add 2 more to get your number of hydrogens. As an example, if you have 12 carbon atoms, the formula will be C12, and then H, you do 2 times 12, 24, plus 2, 26. Now we're going to go through some quick questions. What is the formula for propane? This is the bit where you type in the chat. We're going to have a lot of these questions, so you'll need to be on it. All right, so the formula for propane, as you can see, is 3 carbons, so it'll be C3H8. Butane, it's a similar, it's exactly the same principle. Butane contains 4 carbons, and that means it will contain 10 hydrogens. Yes, I see a couple of you have answered. Now, the simplest hydrocarbon is methane. Its structure can be represented as such. So methane, it has 1 carbon and therefore 4 hydrogens. Draw the structure of ethane. So you should have a piece of paper with you and a pen, because we will have a lot of exam questions that you should probably try to answer, and then we'll go through the mark scheme afterwards. Now, this one's not hard. We have C bonded to a C, and remember, each carbon has 4, 2, 3, and then each of these will have a hydrogen. Excuse my handwriting. There we go. So that's what you should have got. It's a very easy exam question. That should not be hard. Right. Now, identify the following molecule, so name it. What is this molecule? Quickly type it in the chat. We can move on so that I know that you lot can identify and understand this properly. Well, there we go. Seems like we've woken up. Good. So yes, this is butane. And this one, yep, a couple more of you answer as well, then I'll move on. All right, so yeah, this is propane. Now we'll move on to focus on the properties of hydrocarbons. There we go. There's a huge variety of them. Some of them are quite small, and then these short chain molecules tend to be the most useful in life, in industry, and whatnot. Now, the properties of hydrocarbons vary depending on their chain length. And so you need to understand variable of chain length, how the properties of hydrocarbon change. Now, the first thing we're going to look at is boiling point. So as boiling point increases, the chain length increases as well. This is one of the times where it's good to understand it rather than just memorize it. Boiling point, obviously from a liquid to a gas. And for this to happen, bonds need to be broken. The more bonds there are, the harder it is to break. So more energy is needed to break these bonds. So the boiling point would increase. Now, viscosity is how thick a fluid is. So as an example, water would be less viscous as it's runny, and then honey would be more viscous as it's thick. Now, as chain length increases with viscosity, viscosity also increases. This is probably a logical extrapolation of this principle. And so, yeah, as viscosity increases, so does the chain of hydrocarbons. Now, in terms of flammability, this obviously means how easily it burns. The shorter the carbon length, the easier it does burn. Again, that's a pretty logical explanation. So yeah, remember, the shorter the hydrocarbon length, the higher the flammability. As you can see on the left at the bottom, the longer carbon chains often come up with a smoky flame as well, because it can't catch fire as easily. And so it needs to produce something else other than flames in order to become flammable. Now, in terms of volatility, this means the tendency to turn into a gas. The shorter the hydrocarbon chain, the higher the volatility. So the shorter the hydrocarbon chain, the higher the tendency this molecule has to turn into a gas. And this is just a summary of this. So as you can see, we have the size of the molecule, short chain to long chain. Boiling point increases, volatility decreases from short to long, viscosity increases short to long, and flammability decreases short to long. Now, in terms of the properties of hydrocarbons, as we've just gone over, the shorter chain hydrocarbons make good fuels as they ignite easily, burn well, high flammability. And as you saw in that diagram as well, in flammability, it's less smoky as well. These are described as flammable in chemical environments. I'm sure you've seen this symbol before. Yeah. So exam practice. Ethane is an alkane with the formula C2H6. Draw a ring around the correct answer to complete the sentence. Alkanes are hydrocarbons with the general formula. You can just write this on your piece of paper. Shouldn't take more than a couple of seconds. And so the answer is the bottom one. It's CnH2 plus N. Another exam question. Diesel oil is obtained from crude oil. This is something that we're going to go through later. It can be used as a fuel for car engines. The diagram below represents a compound found in diesel oil. What is the formula of this compound? If you lot can type it into the chat, that would be brilliant. And I'll do it along with you as well. So you should be done by now. If you're not, it means you're not using the most efficient way. If it does ask you for the formula of a compound like this, because we have the general formula CnH2n plus 2, all we need to do is count the number of carbons. And then once we've calculated the number of carbons, the hydrogens come easily as you just plug the number in to the general formula. Now, What is a covalent bond? Let's see if I have. All right. Please write this on your pieces of paper. This is an important question, both for exam technique and for understanding. So once you have written it on your piece of paper, please type done into the chat, and then I'll move on once all of you have typed done. I'm not going to move on unless you've all done so. Okay, I'm going to answer the question now. So a covalent a covalent bond, I can see some of you typed in the answer in the chat, and that's actually quite useful. What you need to understand is that even though we're talking about covalent bonds in terms of hydrocarbons, the exam technique for this is a general definition of a covalent bond. And so a lot of you have said that it's a bond between non-metals, which is correct, but you need to explain why it's between two non-metals. And so for the marks in this exam question, you will need to include shared electrons. Okay, so electrons is one of them. And then the fact that they're shared is another one. So shared pair of electrons. That would get you both marks. If you do include non-metal and non-metal, that would also probably get you 1 mark, but you need to include the word electrons and shared electrons. Okay. So for those of you that did type it in the chat, that's good, because I can see that you all have a good understanding of what covalent bonds are, so we can move on. Just as if the noise does get too loud, please let me know and I will quickly move to a quieter place. I did not know that they would be working today, so I do apologize for that. But if you are struggling to hear me, I will try and talk as clearly as possible. But if you are struggling to hear me, please type in the chat and I'll quickly go to a quieter room. All right. The next exam practice question is butane C4H10. This is an alkane, as we've said. Please complete the displayed structure of butane. So they've given you 2 carbons, and so C4H10, you just need to include the other 2. And remember, there's my pen, we will have, all right, that's fine. 1 carbon, 2 more carbons, and then this carbon has how many bonds? It has 1 covalent bond, 2 covalent bonds, and so by logic, it can only have 2 more covalent bonds for our hydrogens. And this carbon only has 1 covalent bond, and this means that it can contain 3 more hydrogens. And if you've come up with this as your answer, it's correct. Now, we're not going to take a break. Crude oil. We're going to go through the uses of crude oil, which we looked at in the beginning. Organic compounds, such as hydrocarbons, are used as fuels to run cars, to warm houses, to generate electricity. So as you can see, it's very useful. Fuels are important because, well, extrapolating, they keep you warm and on the move. So pretty much they're essential to our survival. In terms of economics, when oil prices rise, this affects everyone. Now, with chemistry and also sometimes in biology, GCSE, they like to include one or two little economical questions, just so that you understand the real world applications of what you're learning. So countries that produce crude oil can therefore affect the whole world economy by the price they charge for their oil. Just as a little example, with COVID and all of that, if you remember, it's still going on. Fuel, there was a whole fuel crisis. They've raised the prices. It's been the highest in a very long time now. It's like 149, I think. And so this can just illustrates how much of an effect and how important hydrocarbon fuels are. Now, in terms of crude oil, it's a finite resource, so it will run out at some point. It's found in rocks. It was formed over millions of years. And it's tiny ancient sea animals and plants that were buried in the mud. And over time, there are layers upon layers of rock, which were then laid down on top of the mud. And these created a high pressure and temperature environment. And then this resulted in crude oil. Can I just confirm that you guys can only see the PowerPoint? I just got a notification, which I don't quite understand. If you can just type yes into the chat, if you can only see my PowerPoint. All right, cool. So this is a diagram of crude oil, just so you have understandings. We have your little animals and whatnot. And then you have their remains, you have the mud on top. And as those layers increase, we have increased pressure. And then this will come down and down and down, and then form the oil and gas deposits, which can then be extracted as crude oil. Now, crude oil is a dark and smelly liquid that doesn't really hold much relevance, but what is relevant is that it's a mixture of many different carbon compounds. A mixture, as a definition, is contains two or more elements or compounds that are not chemically combined together. This is an important definition. That's why it's got a little light bulb on the right-hand side. They can ask you to define it. They can include it in a question. If they do include it in a question, it probably means it's relevant to the question. So remember, mixture contains two or more elements or compounds, but they're not chemically combined. Now, nearly all of the compounds in crude oil are compounds containing only hydrogen and carbon atoms, so hydrocarbons. And we can separate them into hydrocarbons, even if they have similar boiling points, and these are called fractions. So fractions of crude oil would be these separate hydrocarbons. This whole process is called fractional distillation, which is an important subtopic of your GCSE. Well, that was the key principle of this we just went over. So it's the fact that we can change them into fractions. Yeah. Now, this is what fractional distillation tower looks like in real life. I will use my Where's my pen? Drawer. There we go. Crude oil is inserted and heated at the bottom here. And then this is a fractionating column, by the way, just the name of it. So the column is kept really hot at the bottom and then much cooler at the top. And this obviously creates a difference in temperature. And the crude oil is fed in as a vapor, so it's a gas at first. Then the gases move up the column this way, and the hydrocarbons condense, so from gas to liquid, as they go up because there's a cooling temperature. And so this is obviously dependent on their boiling points. And now in a more official format, each hydrocarbon fraction contains molecules with similar numbers of carbon atoms. Each of these fractions boil at different temperature ranges because of the different sizes of molecules in it. We went over this when we looked at the variation of properties of hydrocarbons based on the number of carbons in them. So as you can see, the crude oil is fed in through this furnace and that forms it into a hot vapor. The crude oil tower, the fractional tower, is kept really hot at the bottom, quite relatively cold at the top. And then as you can see, based on their boiling points, different fractions are formed and then funneled off. So the one with the highest boiling point, the one that turned into liquid quickest, is bitumen, and the highest one is petroleum gas, which I'm sure you're all familiar with. This is just another diagram to illustrate this. All right, we're going to thoroughly now go through the process of fractional distillation. So firstly, the crude oil is heated and fed in near the bottom of a tall tower. As I said before, this is a fractionating column, and the crude oil, as it's heated and fed in, it's heated and fed in as a hot vapor. So remember, it's fed in as a gas. Next, we know that the column is kept very hot at the bottom and much cooler at the top. This means that the temperature decreases as you go up the column. This means that as the gases move up the column and the hydrocarbons will condense when they reach their boiling point. The different fractions are collected at liquids once they've condensed at their different respective levels. And the fractions that are collected from the column is a continuous purpose. Continuous process. So hydrocarbons with the smallest molecules have the lowest boiling points. Again, we went over this near the beginning of the class. So a molecule like methane will come out at top, and there's something very long like decane. Oh my God, excuse me. Something very long like decane will be at the bottom. And then so smaller molecules stay gases the longest, which means that their boiling point from gases to liquids is at a lower temperature. So they are piped out of the cooler top of the column as gases. At the bottom of the column, the fractions have the highest boiling points. They're very quick to form liquids, and they form very thick liquids or solids at room temperature. Once these collected, the fractions need more processing before they can be used, because they're not particularly, they're quite useless in that state. They can't really be used in a lot of industrial processes. So this is just a recap. As we said, crude oil fed in is a hot vapor. It's the fractionating columns hot at the bottom, cool at the top. the vapors will condense at separate boiling points, and then these are fed off as liquids at their respective points in the column. Now, as an exam question, crude oil is a mixture of many different carbon compounds. This can be separated into useful fractions by fractional distillation. Figure 2 shows a column used to separate crude oil. So here you'll need to complete the sentences. Crude oil is heated so that most of the compounds what? And at different temperatures, the compounds cool and what? So make sure you read the sentences very carefully and then answer this question. Either write it down on your piece of paper or type it into the chat. Please have a go at it and let me know once you're done, and only then we're going to move on. There's only a few of you who's responded. I need the others of you to do so as well. All right, so the answers. Crude oil is heated so that most of the compounds evaporate. As we've been through many times, the crude oil is fed in, heated, and then evaporates. So we know that that means it turns from liquid to gas so that it can become a hot vapor. And now at different temperatures, the compounds cool as they go up. And this means that they then condense. We know that condensation is from a gas to a liquid, and this is the only way that they can then be fed off at different points in the fractionating column. It is not freeze, because if it freezes, we know this is liquid to solid. You can't really move the substances as a solid. So at this point, they only condense from gas to liquid. If you understand the process of fractional distillation, this should not be hard, because you know that the processes, the elemental changes are from liquid crude oil to gas, then gases to different liquids based on their boiling points, and then that would be the end of the process. Right. I think we shall have a break now. When we come back, we'll do 3 more questions, exam practice questions on fractional distillation. So ensure that you fully understand this and that you're ready to answer the questions. And then we're going to move on to complete combustion, burning hydrocarbons, and then cracking hydrocarbons. So I'll give you about 10 minutes, come back at about 10:55, and then we will continue. Does anyone have any questions or need me to go over anything again? If so, please let me know now. If not, you may take a break, and I'll see you in 10 minutes. All right, I'm going to assume none of you have any questions, so I'm going to switch off my video and mute, um, and then take our break. I'll see you in a bit. All right, we are going to carry on now with exam practice questions relating to fractional distillation and crude oil. Because we're doing so well for time, I'm going to give you or ensure that all of you have done the exam practice questions, and then we'll go through the answers. All right, so this is the next question. Which fraction is the most viscous? You tick one of the boxes. On the left, you can see the crude oil separations, fractional distillation. This is where you need to apply your knowledge of how the properties of hydrocarbons change based on the length of the carbon chain. So if you can try and remember the relationship between longer hydrocarbons and the viscosity, then you can work out, using that principle, which fraction is the most viscous. If you can type it in the chat, then we will carry on. We've got 4 more of you that need to answer. Okay, the majority of you got this question right. The answer is engine oil. This one. So if you remember, we said that the longer the carbon chain, so the bigger hydrocarbon, the more viscous it is. So that's the relationship, that as you go down, the hydrocarbon increases, the carbon chain increases, and this means that the viscosity also increases. So the 2 answers that people would get logically is either engine oil or petrol. If you do understand the relationships, then you will realize that the longer the carbon chain, the more viscous it is, and therefore the engine oil would be the most viscous out of the options. Just to ensure that we all know all of the relationships, I'm going to go back to this diagram. So from left to right, we're looking at shorter chains, so a smaller amount, number of carbon molecules, carbon atoms, compared to the right-hand side, which is longer chains, so more molecules of carbon atoms joined together. Now, as you can see, the third one down, we're looking at viscosity. which is, it can also be defined as how easily it flows. So as I said before, water compared with honey, honey would have a higher viscosity. And so the relationship is, as the carbon chain increases, the viscosity also increases. Now, looking at the other one in terms of boiling point, this is probably the most logical one. As the chain length increases, the boiling point also increases. Now, the volatility and the flammability are the opposites. So as the chain length increases, the volatility decreases as well as flammability. So this means that short chain hydrocarbons have a higher tendency to turn into gas than long chain hydrocarbons. And then short chain hydrocarbons are more easily flammable than the long chain ones. So the more carbon there is, the harder it is for it to burn, the thicker it is, it has the least tendency to turn into a gas, and it has a higher boiling point. Okay. Now, one way to remember this is you use the fact that you know that a longer chain has a higher boiling point. If you know this, you will be able to extrapolate from that principle that it has a lower flammability, because we know that high boiling point, so from liquid to gas, okay, so from liquid to gas, which is what flammability is. You're starting with a liquid and then you're burning it, and that produces a gas. So if it has a higher boiling point, it would be harder for you to burn it. So that's how you can relate those two. The second one is the tendency that it will turn into a gas. And then with shorter chains, it has a higher volatility. Again, we can extrapolate this from the higher boiling point. As you can see, boiling point refers to the temperature at which liquid boils or the gas condenses. So if the gas condenses at a higher boiling point, it has a lower tendency to turn into that gas. So it would be a liquid for much longer. If it's a liquid for much longer, it means it's less likely when it becomes a gas to condense. Okay. So it's pretty much the same principle as the flammability. As you can see, flammability, liquid to gas, this is exactly the same, to turn into a gas. And then viscosity, you can, well, it's kind of a logical explanation. The longer the chains of hydrocarbon, the bigger the molecules, the more viscous it is. Okay, the harder it is to pour the liquid, to move the liquid. And that's why if you do manage to look at crude oil, it's very thick and viscous. All right, does anyone have any questions about that before we move on? Okay, I'm going to assume you all fully understand that now. Is that not the same question? Okay, right. So I just went through this. Which fraction is the most flammable? So if you remember the relationship that we looked at just now, based on the hydrocarbon length, please type into the chat which is the most flammable. I'm just going to do a little separation so I know. Oh, that's fine. All right. There's still a few more of you that need to answer. All right, the correct answer is refinery gas. Now, as we just looked at, the shorter the hydrocarbon length, the more flammable it is. As we know, as you go up the separating column, the shorter the hydrocarbon length. Okay, so remember, as you go up, the carbon chain length decreases, and as you decrease the hydrocarbon length, it increases in flammability. The most flammable will be refinery gas. As I said before, if you have any questions, please just type it in the chat and I'll answer it. Now, that's the answer. This is quite a long question, so I need you to concentrate and try and write it out. I will go through it thoroughly so that we know, so that you know the answers. Crude oil is separated into useful fractions by fractional distillation. Describe and explain how crude oil is separated into fractions by fractional distillation. You can use the diagram to help you answer the question. It's a 4-mark question, and so I'm going to give you, I should give you 4 minutes, but I'll give you 5 minutes to answer it. Once you have finished, please type done into the chat. Now I'll give you 4 minutes. 4 minutes is a long time. So once the 4 minutes is up, I'm going to go over the answer. If you are done, just type done in the chat. Remember to try and think about what those 4 marks will represent. So if you were to create this question, what would you put as the 4 marks to get 4 points? Another tip I will tell you is if you read the question, it says describe and explain. It doesn't say list, it doesn't say state, it says describe and explain. So you don't necessarily need to go through the whole thing in extreme detail. It is 4 marks, but you can do it more efficiently if you do identify that it says describe and explain. So to this end, if I was answering this question, I would probably point out at least 2 things, depending on how long it took me to answer the question. And then with these two things, I will then describe it. So describe what it is, what the process is, and then explain why it's required. Right, you have about 1.5 minutes. Once you've finished, just click done, and then I will go through the answers. All right, I'm going to go through the answers now. So 1, 2, 3, 4. You should have said that the crude oil vaporizes or evaporates, or the crude oil enters as a vapor. And then the vapor cools as it rises up the tower because the column is cooler at the top. The fractions have different boiling points or condensation points or ranges. That's the describe and then explain that this means that they will condense at different levels in the tower. If you didn't get the majority of the marks, look at the mark scheme. So as I said, we have describe and explain. So we have the description that the crude oil vaporizes, the explanation that then the vapor cools down because the column is cooler at the top. Then we have the description, the fractions have different boiling points, and the explanation, this means that they will condense at different levels in tower. Now, I know we've gone through this, but it is sometimes quite hard to translate it and apply it in a question. This is why we do exam technique questions, practice exam questions, because then you get into the habit of applying your knowledge in terms of questions. One of the main things to look at in all exams is the keywords that they say in the question. So in this one, it's describe and explain. And then you look at the 4 marks that they require. And just make sure that if you look at your answer, so this is probably what you do once you're checking your exam. You look at the 4 marks and then you look at your answer and see if you can identify 4 points that could get you marks. That's probably a good way to check your answers and make sure that you're getting the majority of points marks. Right, now we're going to go over complete combustion, so burning hydrocarbon fuels once we've fractionally distillated them. We talked about the fact that the lighter fractions, the shorter hydrocarbons of crude oil, these are the ones that are the most useful because they are the most flammable, as we went through. So these basically form fuels in petrols and cars, engines and planes. And to do this, to apply the fuel, use the fuel, it needs to combust. And that's the reaction that's happening. It's also an exothermic reaction, as you can see from the lovely GIF that we've put in. When hydrocarbons burn in plenty of air, they transfer lots of energy to the surroundings. That's complete combustion. The hydrogen and carbon in the fuel are oxidized, and this causes them to burn. This is an example of complete combustion. As we can see, it reacts with the oxygen. That's what oxidized is. And it always produces carbon dioxide and water. So these are key points that you do need to remember. With complete combustion, complete combustion, you need plenty of air, you need oxygen, which is in the plenty of air. And then when they burn, they always produce carbon dioxide and water. Okay, and these will be in the gaseous states. Yeah, except for obviously the methane, which is a liquid. To clear my drawings. When there is incomplete combustion, it means there's not enough oxygen to oxidize all of the carbon and the hydrogen. And this means that we have the same formula as before. There's oxygen, carbon monoxide this time, and water. So on the last one, we could see complete combustion. We have carbon dioxide because there's more oxygen. Okay, we have O2, CO2. And then looking at incomplete combustion, there is not enough oxygen, and therefore we only have CO, which is, as you know, carbon monoxide. And you should also recognize that carbon monoxide particles are toxic. And you can see that in everyday life when cars have a lot of smoke coming out of their exhaust. That would be toxic to breathe in. That's the whole thing with environmental and global warming and stuff like that. If you do remember or you have experienced it, the government is trying to decrease the amount of carbon monoxide that is being released in schools, in and around schools. So obviously when parents drop off children, pick up children, there's going to be a lot of cars, a lot of stationary cars which are turned on. Then incomplete combustion occurs, carbon monoxide is released, and this is toxic to the environment and obviously to the children. Right, we have an exam question here going over what we have just covered. Write a balanced equation for the complete combustion of ethane. Right, so we have ethane, oxygen, carbon dioxide, and water. Now I need you to write the chemical equation and then balance it out. So please do that and then type in the chat when you're done. When you're done, I'll move on. I'll give you about a minute more. Remember to let me know when you're done so that I know when to move on. Don't just wait for other people to do it. All right, that should be enough time. So here we have the balanced equation, balanced chemical equation for the complete combustion of ethane. It's given you the chemical formula C2H6 and the answer C2H6 plus O2 goes to CO2 and H2O. That's just the equation. That's what you should have started off with. And then you need to balance this out. And this comes to 2C2H6 plus 7O2 goes to 4CO2 plus 6H2O. This is just simple balancing of equations. So always start with carbons. We have 2 carbons on this side, and we have 1 carbon here. And so to balance that out, we'll need 2 carbons to come 4, and then 4 carbons here to balance it out. Then we have 6 hydrogens, and so on this side we need 6 hydrogens as well. Now we have H2, okay, but when we look at oxygens, okay, we have 1, 2, 3 on this side, and this is probably the hardest bit of this balancing, okay. So we have 3 oxygens on this side, 2 oxygens on this side, okay, and then if we have 4 CO2, that comes to 8. There we go. And 6 H2Os, that comes to 6. And that's obviously 14. And to balance that out on the left-hand side, we have O2, and therefore we'll need 7 oxygens. All right, the next exam practice question. Petrol contains octane, C8H18, the alkane. Complete the word equation for the reaction of octane with oxygen. This is complete combustion because it says with oxygen, and it doesn't say that there's an incomplete supply of oxygen. So it's the first word equation. So write out the equation. Octane plus what goes to a what and what. All right, I'll go through the answer. So octane plus oxygen goes to carbon dioxide and water. This is the general equation for complete combustion. So whichever hydrocarbon you use, whichever alkane you have, it will always react with oxygen, and with complete combustion, it will always produce carbon dioxide and water. Excuse me. Next, we're going to look at cracking hydrocarbons. So this is once you've produced them in the fractionating column, you've got your different hydrocarbons, and now we need to crack them. If you remember what I said, the longer molecules of hydrocarbons, they're less easy to use. And so to make them more useful, we'll need to crack them from longer molecules to shorter ones. So why are we going to crack hydrocarbons? I'm just going to reiterate what I've said. The heavier fractions are not in high demand since they can't be used in a lot of processes. And these are made up of larger molecules. They're thick liquids with high boiling points, and so to use them, you'd have to use them in an environment with a lot of energy, and this is usually very costly, and so not desirable to use. They're difficult to vaporize, don't burn easily, and so they aren't used as fuels. They're very poor fuels. The larger, the less useful the hydrocarbon molecules can be broken down into smaller, more useful ones, and this process is called cracking. This is a site, you may have seen a couple of these dotted around the place. The process will take place at an oil refinery in steel vessels, which are called crackers, which is quite funny. In the cracker, a heavy fraction distilled from crude oil is heated, and then this is vaporized, the carbons. The vapor is then either passed over a hot catalyst or mixed with steam and heated to a very high temperature. These are fixed conditions which are needed for cracking. Now, the hydrocarbons are cracked as thermal decomposition reactions take place. And as I just said before, these take place when passed over a hot catalyst or when mixed with steam and heated to a very high temperature. When thermal decomposition occurs, the larger molecules split apart to form the smaller, more useful ones. And so as a definition, a key point is that thermal decomposition is the breakdown of a substance caused by heat. So when we look at these two ways of vaporizing, we have a hot catalyst, heat, mixed with steam, which is already hot, and then heated to a very high temperature anyway. Right? So thermal decomposition is the breakdown of a substance caused by heat. Now, applying this to the exam question we looked at earlier, where it said define covalent bonds, a lot of you used topic-specific definitions, but usually with these questions, when it says define this, define that, they're looking for a more general answer, something that you can apply to any stage or any topic in chemistry. So if you define thermal decomposition as the breakdown of crude oil, or which is wrong anyway, or hydrocarbons or long chain hydrocarbons caused by heat, it's correct, yes, but it's not the definition of thermal decomposition generally. An example of cracking is if we use decane, which is a medium-sized alkaline molecule, but still it's not that useful. We can crack it down into more useful hydrocarbons. It's heated to 500 degrees centigrade with a catalyst, and then it breaks down. One of the molecules it produces is octane, and that's C8H10, which is used in petrol. Ethene is also made, which the chemical industry can use to produce polymers and other chemicals such as solvents. We will go through polymers, and they're very useful since they can be made into plastic, so water bottles and such. So this is the chemical and displayed equation. We have C10H22 and then octane C8H18. Sorry, yeah, CH18, not what I said earlier. And then we also produce C2H4, which is ethene. As we can see, it's quite logical, since if you have C8 at the beginning, we have H10 in the decane, and that means that there are two carbons left over. And then we can deduct that means that it needs to be C2H4. Okay, if you have a look at what we've done here, we have alkanes used as fuels and ethene, which is an alkene, right? And alkenes are the ones that can be used to make polymers. Alkanes cannot be used to make polymers. It's only alkenes. Okay, so only alkenes can form polymers. This is quite important because we're going to go through it later. Right. Cracking produces different types of molecules. One of these molecules is pentane. This obviously means that it has 5 carbons, as we've went through the naming of hydrocarbons at the beginning. And the last part of its name, ane, shows that it's an alkane. This means that we know that we can use that general equation which we had before, Cn H2N plus 2. And so if you have 5 carbon atoms, we're going to have 12 hydrogen atoms. Like all other alkanes, pentane is a saturated hydrocarbon, so its molecules have as many hydrocarbons as possible, using the fact that carbon can only have 4 bonds. At the bottom, we can see the reaction of decane when it's heated to 500 and then pass over a catalyst. If it produces pentane, it can also produce propene and ethene. Remember, they have enes at the end, so they're alkenes, not alkanes. This means that their chemical formulas are different, and we're going to go through alkanes later on. So we crack hydrocarbons, we form a shorter chain alkane, and then another type of molecule. The other molecules in this reaction, as I've just gone over, have names that end slightly differently. They end in -ene, and this means that these type of molecules are called alkenes. The different ending tells us that these molecules are unsaturated. So remember that alkanes are saturated. It has as many hydrogens as possible. If it's an alkene, it means that these molecules are unsaturated. Unsaturated compounds contain at least one double bond between their carbon atoms. So they can't have a double bond between hydrogen atoms. They need to have a double bond between carbon atoms. Now, if you need an explanation for this, we know that hydrogen only has one electron in its outer shell, and so it can only form one covalent bond. So you can't have a double covalent bond between carbon and hydrogen. This means that if something is an alkene, meaning it is unsaturated, the double bond needs to be between carbon atoms. And this is represented by C double line for their double bond, and then C again. So as I just said, alkenes have one double covalent bond in their molecules. Because carbon atoms form 4 covalent bonds, it means that the unsaturated molecules have 2 fewer hydrogen atoms in their molecules with the same number of carbon atoms. Here we have ethane as compared to ethene. So ethane, we see here that this carbon has 1, 2, 3, 4, and this carbon has 1, 2, 3, 4 covalent bonds. So that's all good. But then looking at ethene, we need to start with a double bond of the carbons. And this means that looking at this carbon, it has 1, 2 over here. And that means it only has 2 left. And so it can only bond with 2 more hydrogens. And the same principle for this carbon as well. Right, exam practice question. Dodecane, which is otherwise known as C12H26. If you look at the end, it says ane, so it's an alkene, so it's saturated. From crude oil is cracked. This produces ethene. So remember, it's ene C2H4. Complete the equation for this reaction. If you remember what I said earlier, cracking alkanes will always produce another alkane and then another product. We have the other product, which is ethene. And now you need the last one. So complete the equation for this reaction. The second part of the question is give 2 conditions that are needed for cracking. So when I went over those, what 2 things were needed for cracking to happen? Now, whilst you answer that question, I'm going to point something out in the first part. Let's complete the equation for this reaction. We have C12H26 going to C2H4 plus something else. What some people may not realize is that you have 2 molecules of this. Okay, so if you have 2 molecules of ethene, it means naturally that you have 4 carbons. If you have 4 carbons, it means that you will have 8 carbons left. And 8 carbons left gives the alkane C8H18. That is the only acceptable answer because remember, the cracking of alkanes will always produce another alkane and then a separate product. It also says credit any combination of alkanes and alkenes. So you could have C5H12 and C3H6. But as long as you're balancing out the carbons, it's all fine. Now, giving 2 conditions that are needed for cracking, if you remember, the easiest one to remember is a hot or high temperature. You can also write a temperature, but it needs to be in the range of 300 to 900 degrees centigrade. You can't just say heat, because heat could be anything. Like you could heat food up and it would only be, like 20, 25 degrees, if it's quite hot. You need to specify that it's a hot or a high temperature, okay, because that's a relative. So it needs to be relatively hot and relatively high. The second thing you will need is catalyst. They accept a named catalyst if you do want to do that. But I wouldn't, I'd just say catalyst. Or it needs to be allowed to mix with steam. This is an alternative second marking point. Right. Now we're going to move on to alkenes. As I just said, they are also organic compounds. They contain hydrogen and carbon. The carbon atoms, as with the alkenes, tend to form the backbone of these organic molecules. All alkenes will have a double carbon covalent bond in their molecule. And the double covalent carbon bond grouping is an example of a functional group. Now we have various functional groups. The first one we encountered during this session are alkanes. So alkanes with the C and the C with the 1 bond to the H, that's a functional group. And then this C double bond C is also a functional group, and it represents alkenes. A functional group gives a family of organic compounds their characteristic reactions. So that's quite important to realize. Any functional group and all of the organic compounds relating to that functional group, it gives their characteristic reactions. So all of the reactions and the characteristics that it displays are similar to all of the organic compounds in a functional group. A family of organic compounds is also called a homologous series. So functional groups are also called homologous series. Successive members of a homologous series differ from each other by an extra carbon atom that then has 2 hydrogen atoms bonded to it. It's fairly self-explanatory if I explain it like this. So homologous series differ from each other by an extra carbon atom each time the series increases. So here you'll start with two carbons, and then the next compound in the homologous series will therefore need to have 3 carbon compounds, and then the next compound in the series will then have 4, and so on and so forth. When using these extra carbons, you need to make sure that these carbons then have the hydrogen atoms bonded to them. So you don't add another double bond, because in the homologous series, they only differ by our extra carbon and then the 2 hydrogen atoms bonded to it, or 3 in this case. The general pattern and formula of alkenes, so their general formula is CnH2n. So whatever the number, what is happening here? There. Whatever the number of carbons you have, just double it, and then you have the hydrogens. Now, if you remember, the general equation for alkanes is a bit different. So if you have ane at the end, and the general formula was CnH2n plus 2. Right, and then alkenes are just CnH2n. What is happening? Right, so we know that alkenes all have the suffix -ene. We have a little light bulb there, which means it's important to realize that a family of organic compounds are called a homologous series. And remember, a homologous series relating to a family, and a family of organic compounds has a functional group between them, common between them. These are 3 compounds that follow each other in a homologous series. So remember, we start with 2 carbons, you add another carbon, and then the next one you'll have another carbon. And then these are the names. So you have ethene, propene, and butene. As you can see, C2, C3, C4. And using the general equation of alkenes, we have CnH2n. And so using that, we have C2H4, C3H6, and C4H8. And as you can see, we have our functional group in each of them: a double carbon bond, and double carbon bond. I hope that's clear to all of you. Remember, you can always ask questions or ask me to go over something if you need clarification. The next compound in our homologous series after butene has C4. The next one would need C5, and this is pentene. As you can see with pentene, we have 1, 2, 3, 4, 5 carbons. We have our double carbon-carbon bond, and then using our general formula, it should be C5H10, and we can see that there are 10 hydrogens connected. Now, exam practice. Draw the bonds to complete the displayed structure of ethene. I'm going to give you about 30 seconds to do this, and then I'll go over the answer. All right, so the answer for this, draw the bonds to complete the displayed structure of ethene. We have our functional group CC double bond, and that is the correct answer. So as you can see, we have ethene, it's an alkene, so we know it's CnH2n. This means it's C2H4. And we can see we have 2 carbons and 4 hydrogens. You also remember that ethene has the characteristic CC double bond. And therefore, to complete this, you'll have carbon with its double bond to another carbon. Now, before we move on, I'm going to quickly go through what we have covered so far. And then, because we've been going for about an hour now, we're going to have lunch. And then after lunch, we'll carry on. And yeah, then we have reactions of alkenes afterwards, cracking them. Where are we? There you go. Reactions of alkenes. And then we're going to start looking at polymers as well, as I mentioned before. And then we'll go through some exam questions and then look at alcohols. And then after alcohols, we'll go through a lot of quite a few exam questions to solidify your knowledge and application of knowledge. And then that will be today's session. So does anyone have any questions on the structure of alkene, the structure of alkanes, cracking hydrocarbons, fractional distillation, combustion, incomplete or complete? If you do, type it in the chat. Whilst this happens, I'm just going to run through what we've done so far. And then we will have lunch and then come back and then complete the rest of the session. So the main focus of today was crude oil. As we know, it has a lot of uses. The chemicals play a major part in our lives. And remember, the carbon atoms, they form chains and rings. We're focusing on the chains at the moment, obviously, and that forms the skeleton of organic molecules. As we can see here, we have the periodic table, we have carbon with non-metals, and we know how the periodic table works with the mass number at the top, the atomic number on the bottom. Carbon uses covalent bonding, and as we can see on the right-hand side, it has 4 electrons on its outer shell, and therefore it can bond with 4 covalent bonds. So carbon is in group 4, 4 electrons in its outer shell. These bonds can be single, double, or triple. And carbon atoms bond to other carbon atoms to form our long chains. Now, hydrocarbon is a compound that contains hydrogen and carbon only. Remember that. And then a common group of hydrocarbons are alkanes. All their names end in ane. First part of each alkane tells you how many carbon atoms are there. You have methane, ethane, propane, butane. And remember, these prefixes also apply to the alkenes. But remember, with alkenes, you cannot have one carbon atom because all alkenes will need that carbon-carbon double bond. So you start with ethene, then obviously propene, butene, pentene, and so on. So remember that. If you know your knowledge, you'll know it's not possible to have methene because the one carbon atom has no double bond with any other carbon atom. Here we have examples: methane and ethane, propane and butane, 3 carbons, 4 carbons. You can use an acronyms if you want, or you can create up your own ways. I had quite a weird way, as I mentioned before. So alkanes are saturated hydrocarbons, which all the carbon bonds are single covalent bonds. This means that they contain as many hydrogen atoms as possible in each molecule, but remember they also need to bind to each other as well. This means that no more hydrogen atoms can be added. It's not possible to add any more. The general formula for alkanes is as follows. It's CnH2n plus 2. So which means for every carbon atoms, there are doubled and then 2 more hydrogen atoms in the molecule. These are just examples. Then we went through the formula of propane and the formula of butane. Now, properties of hydrocarbons. There's a great variety of them. Some are small, which we now know, and these short chain molecules make up the most useful hydrocarbons. Yeah, and the properties of hydrocarbons vary depending on their chain length. This is where some of you got a little bit confused, so I'll read it again. The properties of our hydrocarbons, depending on the number of carbons which are there, vary. So it changes based on whether they're longer or shorter chains. We go with our summary diagram. As the chains increase in size, boiling point increases, its tendency to turn into a gas decreases, its viscosity increases, so it's harder to flow, and its flammability decreases, so it's less easy to burn. This is something you can commit to memory if you wish, and then you can apply your knowledge. And that's probably one of the easier ways with these varying properties. Or you can try to understand it on a deeper level. We have a higher boiling point. A higher boiling point means it has less of a tendency to turn into a gas since it needs more energy. It's more viscous because there are more carbons, they're bigger molecules, and it burns less easily because there needs a lot more oxygen to be able to oxidize the more carbons and the more hydrogens. Now, properties of hydrocarbons, these shorter ones ignite easily, burn well compared to the larger ones, and these are described as flammable. These are exam questions which we went through. Now, just as some extra knowledge, they're used to fuel cars, warm homes, generate electricity, and so they're really essential to our living. This means that countries that produce crude oil can affect the whole world economy and all of our lives as well. Crude oil is a finite resource found in rocks, and that's a key point. We have a little light bulb. Make sure you know that it's found in rocks, and make sure you know that it's a finite resource, so it will run out at some point. This is a diagram just going over how it forms. So you have your little animals, which then go to the bottom of the sea once they've died, and they have a layer of remains. And then as there's more pressure with the sand and the silt, it will press down on the remains, and then crude oil is produced. Remember, crude oil is a mixture of many different carbon compounds. A mixture contains 2 or more compounds that are not chemically combined together. Again, we have our little light bulb, so remember that this is what occurs. And if they ask you to define a mixture, the key part is that there's a few compounds and that they are not chemically combined. Now, crude oil is separated in a process called fractional distillation. We have our fractionating column. Each of these fractions boil at different temperature ranges. We know that boiling point varies because of the length of hydrocarbon, and therefore the fractions will do the same. As you can see on the right-hand side, we have our diagram. Crude oil comes in as a vapor, and then as the vapor goes up, the fractionating tower, it becomes cooler and cooler, and then condenses at different points. As it condenses, it's then funneled off and grouped together as their respective hydrocarbons. So the first thing is it's heated, turned into a vapor. Second one is the column is very hot at the bottom, cooler at the top, so temperature decreases as you go up. As temperature decreases, the hydrocarbons condense when they reach their boiling points. So if I just reiterate that, when they reach their boiling points, they condense. And if you remember, longer hydrocarbons have higher boiling points. And as you can see, the hotter environments are at the bottom. So if the hotter environments are at the bottom, the longer hydrocarbons will then condense first. And since obviously there's a lower temperature at the top, this is where the shorter hydrocarbons condense because they have a lower boiling point. They're collected at different levels and in these fractions, and it's just a continuous process. This is what I just went through. Hydrocarbons with the smallest molecules have the lowest boiling points. These were exam practices. Then we looked at complete combustion, which is where hydrocarbons are burnt in plenty of air, not burnt, they burn in plenty of air, and this produces a lot of energy. Complete combustion requires full oxidization, so it needs excess oxygen for the reaction to fully happen. And then this is an equation which shows this. So we have methane reacting with oxygen, and complete combustion always produces carbon dioxide and water. Now, this is different compared to incomplete combustion, which forms carbon monoxide instead of water. And we know that carbon monoxide is toxic. Cracking hydrocarbons, some things we've just gone through now. Some of the heavier fractions are not in high demand. They're not as useful as the smaller ones. And so they need to be cracked into our smaller hydrocarbons. This is done at an oil refinery in steel vessels called crackers. And in the cracker is a heavy fraction, which is our long hydrocarbon distilled from our crude oil. It's then heated to vaporize the hydrocarbons and crack them into smaller, more useful ones. So remember the exam question, it's passed over a hot catalyst, so a catalyst is required, and high temperature. If you look at either of these two processes, the common thing you have is the high temperature, the heat. When it says mixed with steam and heated to a very high temperature, in certain processes, steam does also act as the catalyst. So in both processes, you have your catalyst, you have your very high temperature. As the hydrocarbons are cracked, they undergo thermal decomposition. This results in the larger molecules being split apart. You need to remember thermal decomposition is the breakdown of a substance caused by heat. Okay, that's a definition you need to get familiar with. Now, an example of cracking is when we have decane. It's heated to a high temperature, then used with a catalyst, and it breaks down. It can produce octane and ethene, and these are both useful in industry. And here we have the chemical equation, which we went through. Then we looked at our alkanes that are produced. So when we crack our hydrocarbon alkanes, they will always produce at least one other alkane. And then after that, they will also produce another type of molecule. It's not necessarily always an alkene, but in our situation, when we are looking at this, the other molecules have names that end slightly differently. These are our alkenes. They're unsaturated, which means they contain at least one double bond. If they have one double bond, it means that they can only bind to two other hydrogens. Those are some exam questions. Now, we know that our C double bond is an example of a functional group. Our functional group is our alkenes. And the family of organic compounds that are derived from our functional group, they're also called a homologous series. And successive members of a homologous series differ by an extra carbon. So we'll have 2, 3, 4, 5 carbons, and then another 2 hydrogen atoms bonded to it. The general pattern for alkenes is CnH2n, so you just double the number of carbons that you have. Remember, homologous series is important to remember. Here we have examples of our homologous series: ethene, propene, butene. Then on the next slide, pentene. They, as you can see, they're successive members, which means that they differ by our one carbon, C2, C3, C4, and C5. And then that is what we just went through. Now, does anyone have any questions before we go to lunch? If not, I make it 12:10. We can come back at, how much do we have left? 12:10. 25 minutes, 30 minutes should be enough. So we will return at 12:50 and then we will carry on. All right. Thank you, guys. I shall see you in about 40 minutes. All right, we'll start on the second stint of our lesson. So first, we are going to go over some of the reactions of the alkenes. First of all, combustion. Right, so alkenes do burn, but they burn with a smoky kind of yellowy flame compared to alkenes because there's always incomplete combustion of alkenes. Okay, that's quite important to know. There's always incomplete combustion with alkenes. Working. Right, so for the same reason, they also release less energy per mole in combustion than alkanes. So alkanes, if you remember, it's possible for them to go through complete combustion. But with alkenes, there's always incomplete combustion. So alkanes are used as fuels, whereas alkenes do not, or are not. So if you remember, during complete combustion, you get carbon dioxide and water. However, and just remember with incomplete, it's carbon monoxide. So if we were to correct this, we would get rid of the dioxide and put the monoxide, and that would be in complete combustion if we were to talk about alkenes. So another type of chemical reaction of alkenes, more on a molecular level, are addition reactions. As we can see on the left, we have ethane, and on the right, we have ethene. The difference between them are two extra hydrogen molecules. And so the alkenes are far more reactive. Alkenes, are far more reactive than the alkanes. This is quite a logical extrapolation because alkenes have the ability to lose that double bond, then add the two more hydrogen bonds to become saturated. The fact that alkenes are unsaturated means that they're far more reactive. Molecules that react with alkene add across their double bond. Now, we can see here we have an alkene molecule and then a molecule that reacts with alkene. And then the result of this are the two extra molecules are added. So instead of the double carbon bond, that becomes a single carbon bond. And that means that each carbon, instead of only being able to bind to two other molecules each, they're now, because of the single carbon bond, they can bind to three. And then this is where we get our extra two molecules. Now, an example of this is reaction with halogens. And so we can use this with bromine water. And this is used as a test to see if an organic compound is unsaturated. So as I said before, the fact that it's unsaturated means that there can be more bonds added. And if we react it with bromine, which is a halogen, we can test whether the alkene is an alkane. So a positive test for an unsaturated hydrocarbon is if you have the unsaturated hydrocarbon on the right-hand side, and then you add the bromine water, it will decolorize. So bromine water is originally orange. Bromine is originally orange. Then if you add it to a solution, if you add it to a saturated solution, such as an alkane, the bromine stays orange. If you add it to an unsaturated solution, such as alkene, it will then react with that hydrocarbon, and then the orange bromine will turn colorless. Since the alkanes do not react with bromine water, this can be used as a test to distinguish between alkenes and alkanes. Now, let me move this up here so that I can see what's going on. Move this. All right. So also just as a note, bromine, if we look at the periodic table, it's in group 7 of the periodic table. And we'll just go back to that. Yeah, as we can see, it's in group 7 of the periodic table. And those count as halogens. Right, back to where we were. All right. Now, this is a displayed reaction formula with the methane reacting with bromine. As you can see, the bromines are now added across the double bond so that we have a carbon-carbon single bond, and then the bromines replacing that double bond with 2 more single bonds. We can see on the right-hand side that this compound is now saturated because we cannot add any other compounds or atoms or molecules to the products that we've created, since there are now, for each carbon, 4 single covalent bonds. This substance on the right is called dibromoethane. This is quite derivative since you have 2 bromines, so it's dibromo. And as you can see, there's 2 carbons, so we have the eth. And because this is saturated, it's ethane. So it's quite derivative of all the rules that we have gone through so far. That's it. There we have the chemical equation, C2H4, Br2, C2H4, Br2. The halogens always come after this carbons and hydrogens. Usually in all compounds, or in all compounds or molecules, when you're writing them chemically, you will always have carbon first, hydrogen second, and then if oxygen is present in the molecule, oxygen will be third, and then you'll have whatever else is in the molecule. At the bottom of the screen, we can see the reaction that takes place visually. So the bromine water on the left is added to the alkene, and then this reaction takes place, and the result that we get is the orange bromine turns colorless, and that's a positive result of our bromine test. As an exam practice question, this is quite an easy one. What is the color change when bromine water reacts with ethene? It would be orange to colorless, as we've just been through. If it were to say what is the color change when bromine water reacts with ethane, for example, there should be another option that says orange, orange to orange, or no change. Excuse my handwriting. And then that would be correct if that was ethane instead. As we can see, there we go, that's the correct answer. Now, the second reaction that we're going to go through is the reaction with hydrogen. As we know, alkenes are unsaturated compounds, and because of the double carbon bond, their molecules do not contain the maximum number of hydrogen atoms possible in a hydrocarbon molecule. It follows the same concept that we've just done with halogens, but we're now using hydrogen. So what happens when we add hydrogen to ethene? As you can see, we've got the displayed formula of ethene. And this is the result. So we have our ethene here, and bear in mind it's unsaturated, so we can add more bonds. We have hydrogen here, which is the reaction we're focusing on. And then at the end product is ethane. As we know, ethane, we have ane, it's an alkane, and this means it is saturated, which signifies the end of the reaction. This process is called hydrogenation, and for it to occur, we have specific conditions that it needs to undergo. So a nickel catalyst must always be used, and the temperature should be heated up to 150 degrees centigrade. That's what I just said. So we always need nickel catalyst, we always need high temperature of 150 degrees, and when it reacts with hydrogen, it's hydrogenation. So there's a specific term that might crop up in your exam questions, and then you should recognize hydrogenation, hydrogen reacting with ethene or reacting with any other alkene to create an alkane, such as ethane. The third reaction that you'll need to know is reaction with water. When it does react with water, we use steam. We don't use liquid water. And this is clearly called hydration. So just from what we've just done, the recap, we've got reactions with halogens. Then we've got hydrogenation, which is with hydrogen. And then now we have the reaction with water or steam, which is called hydration. Ethanol is an alcohol, which we know, and it's used as a fuel or a solvent, and this can be made from ethene gas. Ethene gas can react with steam to make ethanol. This reaction requires high energy and a catalyst. So this is the word equation. We have ethene plus steam, otherwise known as water in a gaseous state, and this produces ethanol. When we look at the chemical equation, it makes sense because we have our ethene, and we know the chemical formula of that. We have our steam, which is water, and we know that ethanol, signifying an alcohol. So all alcohols will have an OH functional group. If you remember what we said about functional groups, it's a family of compounds with similar reactivity and characteristics. And so whenever you see ol at the end of something, it's signifying an alcohol, and all alcohols have an OH group. So obviously we have the O that comes from the water and the H, which comes from the hydrogen. If we look, we only have one hydrogen here because that's the functional group, which means that we will have another hydrogen that needs to bind to the ethene. And that's where we see 4 hydrogens here and 5 hydrogens here. So to recap, we have 3 main types of reactions: hydration, hydrogenation, and the halogen reactions. Okay. Now, can you just write in the chat, what are the conditions needed for hydrogenation? So what are the conditions? Oh Lord. Right, so just type it in the chat. What are the conditions needed for hydrogenation to occur when alkenes are reacting with hydrogen? There should be 2 conditions. Just write it out. Good, I've got a couple of answers. We need a couple more. All right, yes. So for hydrogenation to occur, you'll need a nickel catalyst and a high temperature, which is 150 degrees or above, but just put 150 to be safe. Next, we are going to look at polymers. I've mentioned this before in this lesson, but we'll go through it in much more detail now. With polymers, the process that they go through to create them is called polymerization. And the most common type of polymerization is addition polymerization. Now, a lot of people understand and they can kind of recognize when this happens, but with a lot of exam questions, it will ask you to write out the chemical formula of an addition polymerization reaction. And there are specific steps and specific parts of that question which need to be answered properly, which you need to include. And a lot of people either forget or get mixed up between them. So although this is quite a simple concept, when you apply it, it's much harder. And if you have the ability to apply it through exam questions, which we're going to go through, this should be quite a simple topic for you, and which will obviously need less revision in terms of your GCSEs. Now, we know that the fractional distillation of crude oil and cracking in an oil refinery produces a large range of hydrocarbons. The hydrocarbons that we create, that we want to create, are usually quite small. So that's why we have cracking. Crude oil-based products are all around you. As you can see on the right-hand side, it's a lot of plastic, what you consider as plastic. They're used to make a wide variety of things, ranging from cosmetics to explosives. One of the most important ways that chemicals from crude oil are used is to make these polymers with the hydrocarbons. So plastic used in everyday are made up of huge molecules made up from lots of small molecules joined together. This is another reason why cracking our hydrocarbons from larger carbon molecules to smaller carbon molecules are desirable, because then you can add all of these small molecules together and it creates a huge, strong structure. These small molecules each are called monomers. The huge molecule they make are called polymers. And here we can see the derivative etymology. Mono means one, poly means many. By using different monomers, you can make various types of polymers, and they each have very different properties based on which ones you use. This is an example. We have ethene on the left, and then if you put loads of ethenes together, you create polyethene. And the same with propene and creating polypropene. It's the same concept used for all addition polymerization. And I'll go through why the addition is important in this process. So ethene is the smallest unsaturated hydrocarbon molecule. We know that unsaturated hydrocarbon molecules are also known as alkenes. It can be used to make polymers such as polyethylene or polyethylene for short. Polyethylene is a really useful plastic as it's strong, it's malleable, it's easy to shape, and it is transparent, so you can add coloring to it if you wish. Now, with ethene monomers, you create polyethylene, but we also have propene, C3H6, which is another alkene, as we know. And this can be used to make the polymer polypropene. Polypropylene is also a very strong, tough plastic, and it can be used to make many things, including carpets and milk crates and even ropes. So compared to polyethylene, polypropylene is much, much stronger and rigid. We're going to go through how these monomers join together. The double covalent bonds between the two carbon atoms in each molecule opens up. As we saw in the reactions that we just did about alkenes, so the hydration reaction, the hydrogenation reaction, and then the reaction with halogens, we had an addition reaction happening. What we saw was the double bond CC with the double covalent bond in between. That was removed and replaced by two more bonds, which connected to either like bromine halogens or more hydrogens or another hydrogen and an OH group. When you're making monomers, the alkene molecules each join together. So we'll have a look at this. It's replaced by a single carbon-carbon covalent bond between the two carbon atoms. And in this way, you can just create a huge link of carbon molecules together. But bear in mind that these molecules are all started out as alkenes. So if you have an alkene monomer, an alkene polymer, sorry, you do not name it. So say you have, if we have polyethylene here, where was it? We have polyethylene on the right-hand side. What you shouldn't do is count carbons, 1, 2, 3, 4, 5, 6. Say there's 7 carbons here. You shouldn't then call it an alkane. Because with polymers, they can only be drawn with so many carbons. But in reality, this goes on for a very, very, very long time on either side. Clear that. To where we were. The polymer chains make up a backbone of these carbon atoms. And this type of reaction that forms it is called addition polymerization. And the polymer that is formed generally is known as an addition polymer. This is how the reaction occurs. This is addition polymerization. Here we have our lots of small molecules, and we can see the double bonds everywhere. And then here they join together to form our polymer. And here we can see this double bond is now a single bond. Since it's now a single bond, these carbon atoms have one extra bond that they can make. Yeah, because they have one bond here, one bond here, and one bond here. That's 3. And they have the availability for one more bond. And then that bond takes place here and it connects to another carbon. In the same way, the second carbon over here, the double bond is now a single bond, same one. And then the extra bond is used this way to connect to this carbon. Then in the same way, we go on and on. This carbon connects to this carbon because it needs 3 bonds. Once that is removed, and so on and so forth. So we can see that all of these monomers with their double bonds, they form the polymers, and we have lots and lots of single covalent bonds. We have a long chain of carbons, which have then, the blue lines represent the new bonds that have been formed between them. Now, this may look quite daunting, but we're going to go through it slowly. Here we have your ethene monomers, right? That's exactly what we looked at before, just in a different format. Okay, these are all ethene monomers. They just look a little bit different. They're just displayed differently. We still have the 2 carbons, the double bond, and then the 2 hydrogens bound to each. And then the result of that is our polyethene, where each of the double bonds are now single bonds. So here, here, and here. And then because these are now single bonds, the carbons have 1 more bond that they can use. And then these are the new bonds that they use to connect to the next ethene monomer to create polyethene, which is a really, really long strand of carbon molecules. This is what I was talking about earlier with exam questions. You can write this more simply as a chemical equation as follows. So, as we can see, at the top, we have our ethene monomers, but it's kind of, it doesn't really represent it properly if you just write ETC. That's not really chemically correct. ETC is not a, it's not a scientifically correct way of explaining that there's a lot of monomers. So what we can use our monomer. So 1 molecule of our monomer, and then we just write an N, which represents any number. So it will represent a really, really large number, which then forms their long polymer. And then the polymer that's created, you then show 1 molecule of that polymer. Here we can see the double bond is now a single bond. And then the 2 extra bonds that this carbon and this carbon can now use are extended outside the brackets. The fact that they're extended outside the brackets shows that it will just connect from that molecule to the same molecule over and over again. After you put the brackets, we have the N again, which relates to this N, and N is just a large number. I hope that makes sense. That's another way of writing it. You have your repeating unit of polyethene, which is here. So this is relating to the polymer, not the monomer. And then from this, we can then show it chemically by using these brackets. It doesn't matter whether they're squared or curved, but what does matter is that these bonds extend outside the brackets and outside the brackets to show the extra bond. And then you write your little N here. And that's the correct way to show a polymer chemically. Other examples, here we have the monomer ethene, and I'm going to ask you to then draw out the repeating unit, right? And that would be, the repeating unit would be this, that's the repeating unit, okay? Then the structure of the polymer, is this. And then final uses of polymer, I will just go through. But the 2 things that I want you to now do are repeating units and structure of polymer. And as I just went through now, that's the repeating unit without the brackets, but it's representative of the polymer. And then the structural, chemically correct way of displaying it with your brackets and the bonds going outside the brackets and your little N down here. Now, so get your piece of paper, write down the repeating unit of ethene, the polymer of ethene, and then the structure of the polymer. And then I'll go through it in a minute. Okay, we'll now go through it. The repeating unit is as such: we have lost the double bond, and then we have the two bonds on either side of the carbons, which will then bind to another repeating unit. And the structure of the polymer, we have our brackets, we have the extending bonds, and then our little n on the side. The uses of polyethylene are things such as bags, crates, and boxes. And it's quite an important polymer, which is used in everyday situations, as I'm sure you're aware. The next one we're going to do is chloroethene. So I'd like you to draw the repeating unit of the polymer and the structure of the polymer. This is where it starts to get a little bit more confusing, but if you use the same logic, get rid of the double bond, use two double, each carbon will have one extra bond, which extends on either side. And then these will then connect to another chloroethene molecule that is being included in the polymer. So write down on your piece of paper your repeating units of the polymer and then the structure of your polymer. And then in a few seconds, I'm going to go through it. Right, so the repeating units, we have our basic structure with the two bonds on either side, the structure of the polymer with the brackets, the bonds extended, and then the little n. We have our hydrogens and chlorine in the same place throughout. So once you get into the habit of doing these, it's quite easy. It'll become, a habit. You'll just write it straight out. What you do need to focus on when they're asking the question, are they asking for the monomer? Are they asking for the repeat unit of the polymer? Or are they asking for the structure of the polymer? If you are writing an equation, remember that the monomer will also have their n on this side to represent our large number. Next, we have propene, which can be displayed as such. I'll go through them now because it's fairly self-explanatory, as we have just done. So this will be polypropene. This is used for carpets, crates, and boxes. Now, what does get confusing sometimes is if in the exam paper, they will write it like this. I'll take my time because it is quite confusing. They could potentially write it like this, which is very annoying. Right, when you look at this, it just seems very messy. It seems like the hydrogens aren't in the right place, or it doesn't look like it can be made into a polymer. When you are drawing monomers and polymers, the best thing to do would have your carbons in the middle, and then you just have single bonds on the top and the bottom. That's the simplest way, the easiest and clearer way for you to do that. If you're given something like this, start with the double bond in the middle. That's where you should always start. So you have your double carbon bond in the middle, then you look at what the first carbon is bonded to. It's bonded to two hydrogens. So you put one hydrogen up here and another hydrogen down here. Then you look at your second carbon. This is your second carbon, since it's the one included in the double bond. Now you need to look at what this carbon alone is bonded to. So obviously it only has 2 more bonds because there are 2 bonds on this side. One of the bonds is to a hydrogen and the other bond is to another carbon. So we're going to put a hydrogen down here. And then we put the other carbon here. But this carbon molecule is not just carbon. It's carbon with 3 hydrogens on it. And then we can write that as CH3. Okay. Now, sometimes if you followed that, good. Sometimes they can be even more annoying. And they might put something like, so you have your C, H, and H. They might put a C, what to draw? They might put a chlorine or a bromine or something here. Now this just makes it so much more confusing because you've got a lot of things going on, but you follow the same process. Start with your carbon-carbon double bond. Here is your carbon-carbon double bond in the middle. Now on the left, this carbon still has 2 hydrogens, all good. On the right, this carbon here is bonded to 1 hydrogen still, all good. We have our 1 hydrogen. But now this is bonded to another carbon, still all good. But now this carbon molecule here, it's not just hydrogens it's bonded to. It has 2 hydrogens, so H2, and a chlorine molecule. So this is how you should always represent your monomers. Your 2 double bonds, your 1 double bond, and then up and down, and look at just what the double bonded carbons are connected to, then write it out as such. Now, I hope that makes sense. This is a question about polymers. The formation of polyethylene can be represented as such. And here, as you can see, we've got the ends and we've got the brackets. What is the name of this type of reaction? This shouldn't be hard. It's an addition reaction because we are adding 2 more bonds on either side. Okay. Now, this compound is used to make a polymer. State the name of this compound. Now, you can type it in the chat. State the name of this compound. This is where I said they display it in a really weird way. But if you think about it, if you look at the structure, you can open it up so you see all of the bonds. And then let me know what is the name of this compound. Right, correct. It is Pro-P. Because you can see we have 3 carbons, so that's prop, and we have 1 double bond, so it's propene. Now we have repeating units of 2 polymers, P and Q, are shown in the figure below. Draw the structure of the monomer used to form P, and then name the type of polymerization involved. I'll give you a couple of minutes to do that. So things to focus on this is that it's showing you repeating units of polymers. So they're not showing you any monomers so far. These are just the repeating units. And the question is draw the structure of the monomer which is used to form polymer P, and then name the type of polymerization involved. I'll give you about 30 seconds to do that, and then we will move on. All right, we'll go through the answer now. So the structure that you should have got is the structure that's shown here, and the type of polymerization is addition polymerization, as we know. Please let me know if you did get this structure. If you did not get this structure and you don't understand how we got here, please let me know. If not, we're going to move on to alcohols. All right, we'll move on to alcohols then. So the first thing we're going to look at is the structure of alcohols. Now, we know that both alkanes and alkenes are only made of carbon and hydrogen, so we can call them hydrocarbons. However, there are many more homologous series, functional groups of compounds, organic compounds that also contain other types of atoms. Remember, organic compounds means that there's carbon involved somewhere. Carbon is the backbone of our compounds. Some organic compounds are made up of carbon, hydrogen, and oxygen. As an example, alcohols. If a hydrogen atom is removed from an alkane molecule and it's replaced with an OH group, as I mentioned before, this would give us an alcohol molecule. The OH group of atoms is another example of a functional group. This is an example of an alcohol, and another alcohol, and another alcohol, and another alcohol. As we can see, we have 1 carbon, 2 carbons, 3 carbons, 4 carbons. So this is a homologous series with the addition of 1 carbon and then 2 hydrogen bonds extra for each in the series. The uses of alcohol, especially ethanol, are commonly used in everyday products. Ethanol is the main alcohol in alcoholic drinks. And there is a specific process to make ethanol. It's made by fermenting sugars from plant material with yeast. So it's fermentation with yeast. Ethanol is made by fermentation and it's termed a biofuel. So ethanol is termed a biofuel. To do this, we start off with glucose and we use yeast. And this produces ethanol and carbon dioxide. So we're talking about alcohols here, remember? So we're not talking about alkenes or alkanes anymore. We're just talking about the production of alcohols. One way to produce alcohol, specifically ethanol, is by fermenting glucose, fermenting sugars with yeast, and then this creates our ethanol and carbon dioxide as a side product as well. And this process is called fermentation. That is the balanced chemical equation. So we have C6H12O6, which is glucose. And then that goes to carbon dioxide, CO2, and then ethanol, which is C2H5OH. Now we know this is ethanol, as if I go back to our alcohols, we have C2 on this one, H5, sorry. So, okay, so this is the thing with alcohols. When you're writing them in a chemical equation, start off with the C's, we have 2 C's. Then start off with the H that are bound to the carbons. So we have 5 hydrogens only bound to carbons. 1, 2, 3, 4, 5. And then the functional group needs to be written on its own. This hydrogen is not bound to any carbon, it's bound to the oxygen. And so at the end of the formula, we write OH. Now, we're going to now look at reactions of the alkenes to produce ethanol. Now we're back to alkenes and alcohol now. The last one was just the production of alcohol using glucose. So that's called fermentation. And now this is the reaction of alkenes with alcohol, no, not with alcohol, to produce alcohol. So a second way that ethanol can also be made is by reacting ethene and steam, but they also need a catalyst. Now remember, we can obtain ethene by cracking the heavy fractions or the long hydrocarbons formed from crude oil. So we have crude oil undergoes a fractional distillation, and then it will produce a long hydrocarbon. We know that long hydrocarbons aren't really useful, they're not desirable. So then the long hydrocarbon, also known as the heavy fractions, they undergo cracking, and then this will produce ethene. And then we use ethene along with steam and our catalysts to produce ethanol. As it says, this method uses up some of the diminishing supplies of crude oil. This is a non-renewable resource. It's a finite resource, as we mentioned earlier. Another reaction of alcohol is combustion. The use of ethanol as fuels shows that the alcohols are flammable. Ethanol is used in spirit burners and can also be used as biofuels in cars. It burns with a clean blue flame. So when you're using your Bunsen burners in school, ethanol is being used because this is a spirit burner. And that's why you get your clean blue flame. If you are using ethanol. If you're not using ethanol, then it's just a normal Bunsen burner. This is the equation of combustion of ethanol. So here, ethanol is now on the left-hand side. We're not producing it, we're using it. And then we combust it with oxygen. And as we know before, complete combustion always produces carbon dioxide and water. And below we have the equation. We have ethanol, C2H5OH, reacting with oxygen, producing carbon dioxide and water. And they've also balanced it out, which is essential if they've asked you to do that in an exam question. Another reaction is a reaction with sodium. So we have alcohol reacting with sodium. Alcohol reacts in a similar way to water as with sodium. So in a similar way, when we have, where is it? There, sodium. So you add ethanol and you have sodium, which is Na. You always produce hydrogen as a product. So you will have H2. And then you produce sodium eth oxide. Okay. Naming this is a little bit trickier. So we're focusing on alcohols. This is our alcohol here. So that's the relevance of alcohols in this equation. We're adding sodium to it. And we know that in a reaction with sodium and alcohol, as a rule, you'll always produce hydrogen. So 2 hydrogens here. And then you're going to use one of your molecules of sodium to replace the hydrogen here. Okay. So this hydrogen is being replaced by a sodium. And because we are producing hydrogen, which is H2, we need to balance out the rest of the equation, which then requires 2 Na, 2 molecules of ethanol, and then 2 molecules of sodium ethoxide. All of these reactions, they're just rules. If you learn the rules of the equations, then they become easier when you look at exam questions. Now, there is a lot of exam questions now to go. Does anyone have any questions before we go through these exam questions? Any questions on alcohols? I can go through it again quickly if you want, and then we'll start the exam questions. No, that's polymers. Still on polymers. Right, here's our alcohols. So alcohols are made up of carbon, hydrogen, and oxygen. Their functional group is OH, and with OH, this would give an alcohol molecule. This OH group is a functional group. These are examples of alcohols. As I said before, the addition of one carbon and two hydrogens means that it's a homologous series. And then the uses of alcohol, it's in alcoholic drinks. It can also be used as fuel and so on. Now we go on to our reactions. The first reaction is producing ethanol. So the production of alcohol. One way we can do that is by fermenting sugar, fermenting glucose with yeast, and then this will produce ethanol and carbon dioxide. Now, the next one we looked at was reaction of alkenes to produce alcohol again, to produce ethanol. So these two are for the production of ethanol. On the left-hand side, the reactants are now an alkene, along with steam and a catalyst, and this would just produce the ethanol, which is different from fermentation, which also produces carbon dioxide, and obviously uses glucose and yeast. The next one we looked at is the reaction of alcohol with oxygen. So alcohol is now a reactant, reacting with oxygen in the form of combustion. As we know, complete combustion produces carbon dioxide and water. The next one is our reaction with sodium. So again, the alcohol is on the left side of the equation. We're adding sodium and we form sodium ethoxide and hydrogen. The naming of sodium ethoxide is fairly simple. You've got your sodium here, so you put that before. It could be any other one as well. You've got your eth because there's two carbons, so that's why there's the eth, and then oxide because you have your oxygen now. It's not ol, so it's not sodium ethanol. That's not correct because you do not have your OH functional group. Instead, you have your oxygen and your sodium. And here's the sodium on the beginning of sodium ethoxide, and then the oxygen at the end of it. Now, exam practice. I need all of you to interact with this because there's a few of them, and we're going to go through all of them to make sure that you know what's going on. Now, methanol can be used in racing cars as an alternative fuel to petrol. Methanol, yeah. Write the chemical equation for the complete combustion of methanol. So first, you need to know the chemical equation of methanol. So we have meth, which indicates the number of carbons, and then ol at the end, which indicates that it's an alcohol and it has an OH group somewhere. So I would start with writing the chemical equation of methanol and then finishing it with the complete combustion. When you're done, please let me know. So that we can move on to our other exam practice questions. Okay, So the answer is here. So methanol, we have the chemical equation. We have our CH3, the one carbon relating to the meth over here, and then the OH group relating to the ol. Complete combustion means that it's oxygen, and it always produces carbon dioxide and water. And then you need to balance the equation as well. The next question. So we'll read it slowly. Most of the hydrocarbons in crude oil are alkanes. Large alkane molecules can be cracked to produce more useful molecules. The equation shows the cracking of dodecane. Give two conditions used to crack large alkane molecules. So what are the two conditions that are required for cracking? Okay, and then the second part of the equation, the products are hexene and ethene. These are alkenes. Now we need to complete the sentence. When alkenes react with bromine water, the color changes from orange to what? And this should be a fairly quick, simple 1 mark and 2 marks, to be honest. Right, going through the answers. The two conditions used to crack large alkane molecules, we have high temperature and we have a catalyst or steam. Steam is a catalyst as well, but it's more specific, so you could write either. The alkenes react with bromine water and the color changes from orange to colorless. You could also say it decolorizes, but you should not write clear or discolored. The safest bet is just to go to colorless, just say colorless. Next, it's a little input of stuff. To make crude oil more useful, it's separated into fractions. Use the correct word from the box to complete each sentence. Crude oil is a what of different substances. The substances in crude oil have different what points, and crude oil is separated by fractional what. Now it's 3 marks, but it should take you no longer than 30 seconds. All right, I'm going to run through the answers. Crude oil is a mixture of different substances. And remember, mixture is 2 or more molecules or compounds that are not chemically bound together. The substances in crude oil have different boiling points. We know this. And crude oil is separated by fractional distillation. Right, next. These are where we have each of our little light bulb things. State, crude oil is a mixture of many saturated hydrocarbons. They can then be separated into fractions by the process of fractional distillation. State what is meant by a hydrocarbon, state what is meant by saturated, and state what is meant by a fraction. Now this is 4 marks. I'm going to give you 2 minutes to do it. And I'll time that now. Actually, I'll give you about a minute. You don't need to type it out because it will take too long. If you write it out, that might be easier. All right, we'll go through the answers now. So a hydrocarbon is a compound of carbon and hydrogen only. So you get 1 mark for each. Saturated means that the compound has single bonds only, or you could say no double bonds, or you could say it contains the maximum number of hydrogen atoms. And a fraction is molecules of a similar chain length. So some of you may be a little bit confused about that, or a lot of people won't get that mark. But remember, there are a lot of fractional distillation creates lots of fractions, and each fraction contains molecules of the same or similar chain lengths. So this question is not saying state what is meant by fractions. It's just one of the fraction, and each fraction contains molecules of similar chain length. Next, we have crude oil is a complex mixture of hydrocarbons, mainly alkanes. The number of carbons in the molecules range from 1 to over 100. How does the boiling point change as the number of carbon atoms in the molecule increases? So as the number of carbon atoms increases, how does the boiling point change? Does it go up or does it go down? Next is name the method used to separate petroleum into fractions. And then it says the simplest hydrocarbon is methane. This structure can be represented. Draw the structure of ethane. This is a total of 3 marks. It shouldn't take you more than about 40 seconds to a minute. Now, to go through the answers, how does the boiling point change as the number of carbon atoms increases? The more carbon atoms, the higher the boiling point temperature. You could say the boiling point increases, or the boiling point is higher. Don't talk about melting point, obviously. The name to separate petroleum into fractions is fractional distillation. And then the structure of ethane is as follows. The next one, bromine water can be used to show that a hydrocarbon is ethene rather than ethane. So that's our experiment. Complete the equation below to show the displayed formula of the product of the reaction between ethene and bromine. So here we need the product, and it's a displayed formula of the product between ethene and bromine. Next is, which is the correct statement about this test? Either the color of ethene is brown, the product is a white precipitate, the product of the reaction is colorless, or the test involves a substitution reaction. All right, to go through the answers, this should be your displayed formula. So the double bond is now a single bond between carbons, and we've added the 2 bromines below. You could put them anywhere, to be honest, as long as they're each connected to 1 carbon and we all have single bonds. Now, the correct statement is that the product of the reaction is colorless. The color of ethene is not brown. The color of bromine water is brown. The product of the reaction is not a white precipitate. That has nothing to do with this reaction. And the test involves a substitution reaction. That's wrong. It involves an addition reaction because we're adding bromine across the carbon-carbon double bond. Next, we have the cracking of large molecules obtained from crude oil is one of the most important processes in an oil refinery. So we're talking about cracking here. Cracking involves the thermal decomposition of large molecules. The diagram below shows an apparatus that can be used to demonstrate cracking in the lab. The porous pot acts as the catalyst in the reaction. So the first part of this question is what happens during thermal decomposition? This was one of the definitions that had the little light next to it, which means it's very important. It's 2 marks, which means it needs 2 essential points for the definition or for the process. All right, so the answer should be what happens during thermal decomposition. We have the molecules are broken down by heat. And that's a very simple definition. And we've got our 2 points because we've got the molecules are broken down. And this happens by using heat. Thermal decomposition requires heat to happen. And that's quite easy to deduce because it has thermal in it. And decomposition, again, it just means the breaking down of molecules. You're decomposing the molecules. The second part of this question, what effect does the porous pot catalyst have on the reaction? This is a 1 mark question. It should not be hard. Don't overthink it. So what effect does the catalyst, the porous pot catalyst, have on the reaction? This shouldn't take more than a second. We know that all catalysts speeds up reactions. So that's all you needed to write. What effect does the porous pot catalyst have on the reaction? Doesn't matter what catalyst it is, porous pot or platinum or anything else, it speeds up the reaction. The final part of this question, complete the equation below for the cracking of the molecule C20H42. So we've got C20H42 and we've cracked it into C12H26, and then you need to complete the equation for the rest of the molecules that are produced. It's a 1 mark question, so you probably only have 1 other product. And the best way to do this is, well, it's simple maths with making sure you have the correct amount of carbons on the left as of the right, and the same amount of hydrogens as well, obviously. And the answer to this is C8H16. So that is 1 mark. Now, that brings us to the end of the session. If anyone has any questions, please let me know. Thank you for listening. I hope you understood it all. And yeah, so if you may leave if you have no questions. If you do, let me know. I'll give you a couple of minutes and then I'll end the session. All right, I'm going to assume none of you have any questions, so I'll end the session. Thank you.